So last time we were looking at a set X which is non-empty and H hereditary sigma ring on X and mu star an outer measure on H. Then we define S bar equals mu star measurable sets. So E belongs to S bar, so this means mu star of A equals mu star of A intersection E comp E plus mu star of A intersection E complement for all A in H, and then we saw this is equivalent to saying greater than or equal to the same thing. Because the other inequality is obvious by subadditivity. And then we proved that S bar is a sigma ring. First we proved it's a ring, then we proved it's a sigma ring. And mu star equal to mu bar equals mu star restricted to S bar is a measure. Okay, so now given X a non-empty set and R a ring and mu a measure on R, then we had a natural extension. So we had a natural mu star, which is the outer measure generated by mu on H of R, which is the smallest hereditary ring containing R. So how was this mu star of E defined? Mu star of E, if you recall, this is equal to inf of set of all sigma mu of EI, I equals 1 to infinity, such that E is contained in union I equals 1 to infinity EI in R. Because every member of the hereditary sigma ring generated by R can be covered by countable elements in the ring, and so you take all such countable covers and then take the corresponding series and then take the infimum. This gives you the natural outer measure generated by R. So now this, if you now define S bar equals mu star measurable sets in H of R, then mu star is a measure on S bar. So we have now got a different set, a sigma ring on which you have a measure coming from the original measure. Now the question is this an extension of the original measure or not? So that is the question which we want to answer, and therefore we have the following proposition. So R a ring of subsets of X non-empty and mu measure on R, mu star induced outer measure on H of R, then if S bar is the collection of mu star measurable sets, we have S of R, the sigma ring generated by R, is itself contained in S bar. Since R is contained in S bar, so and okay, in particular mu bar equal to mu star restricted to S bar is an extension of mu to the sigma ring generated by R, as well as to S bar and is complete with respect to S bar. Okay, so mu bar is a complete measure and it's an extension. So given any ring and a measure, you can extend it by this method of outer measure to a complete measure, and this complete measure also gives you an extension to the sigma ring generated by this. So we have proved almost all of these parts except, so proof only need to show S of R is contained in S bar. All the other things will follow. So enough to show R is contained in S bar. Because if R is contained in S bar is a sigma ring, so it should contain the smallest sigma ring containing R, and therefore it should contain S of R also. So this is the, so it's enough to show that R is contained in S bar. Okay, so let us take, so let E belong to R and let A belong to H of R. So what should to show? In fact, that mu star of A, let us say, is greater than or equal to mu star of A intersection E plus mu star of A intersection E complement. That will show that E is mu star measurable and therefore it belongs to S bar. So R will be in S bar and therefore S of R will also be in S bar. Now, obvious if mu star A is plus infinity. Because this side is infinity, you don't care what is on this side. So assume, without loss of generality, that mu star A is finite. So what is the definition of mu star A? We have already defined it here. So this is the definition of mu star A. If that is finite, that means there exists EI in R such that A is contained in union I equals 1 to infinity EI, and sigma mu of EI I equals 1 to infinity is less than mu star A plus epsilon. So given epsilon positive, there exists EI, so you can find a cover such that this happens. Now we have that mu star equal to mu, because it extends mu, we know that, which is a measure on R. And therefore you have sigma I equals 1 to infinity mu of EI equals sigma I equals 1 to infinity. I can write each of these terms, so I can write mu of E intersection EI plus mu of E, E complement intersection EI. Because it's a measure, each of these sets EI is nothing but the union of disjoint union of EI intersection E and EI intersection E complement. So being a measure, this has to add up now. Now we have also subadditivity of the, now what about E intersection EI? This contains EI intersection E, and similarly union I equals 1 to infinity E complement intersection EI contains A intersection E complement, because union I EI contains A, and therefore by subadditivity of the measure, so by subadditivity what do you have? You have that sigma mu of EI is greater than or equal to mu star of A intersection E plus mu star of A intersection E complement. And therefore, this implies, since mu star of A, we have this relation here, so mu star of A plus epsilon is strictly bigger than mu star of A intersection E plus mu star of A intersection E complement. So you have that epsilon arbitrary implies that mu star of A is therefore greater than or equal to mu star of A intersection E plus mu star of A intersection E complement, and this implies that E belongs to S bar, that is R is contained in S bar, which implies that S of R is also contained in S bar, and the theorem is completely proved. Okay, so this construction of a complete extension of a measure, so this method is due to Caratheodory, so method of Caratheodory. So this is called the Caratheodory extension of a measure. So you get a complete measure on all the measurable sets, and it also extends it to the sigma ring containing the measure. So if you construct a measure on a ring, you can always extend it to the sigma ring, and also you can extend it to a complete measure on a slightly bigger sigma ring. Okay. So remark, suppose mu is sigma finite on R, then we already saw that mu star is sigma finite on H of R, and any element has in H of R has a countable cover from R with each set of finite measure. This we saw this. We already saw this, and therefore this implies that mu bar is sigma finite on S bar and S of R. Okay, so this just a simple observation which we have then. So next, we have the following proposition, and we will see in a moment why it is important. Okay, so mu measure on R, a ring on X non-empty. Mu bar, its extension to S bar and SR by the above method. Okay, so let E belong to H of R. Then we can compute the outer measure of E equals inf of mu bar of F in S bar and F containing E, and this is also equal to inf of mu bar of F belong to S of R, F containing E. So now the mu star measurable, mu star outer measure has a slightly easier formula, but you can do it from S bar, SR or R, whichever way you like. So proof, we'll write down a series of inequalities and the proof will come from that. So mu star of E, what is the definition? This is equal to inf sigma I equals 1 to infinity mu of EI, E contained in union EI, I equals 1 to infinity EI in R. And because of the definition, this is equal to the same, I equals 1 to infinity mu bar of EI, because mu is the same as mu bar, so there is no difference. Now I am going to take, if I take a slightly EI from a bigger set, then I will have more countable covers and therefore the infimum will go down. So this is greater or equal to infimum sigma I equals 1 to infinity mu bar EI, E contained in union I equals 1 to infinity EI, and EI now taken in S of R. Now by subadditivity, this is greater or equal to infimum mu bar of union I equals 1 to infinity EI, E contained in union I equals 1 to infinity EI, EI in S of R. This is just a subadditivity property. Sigma mu bar of EI is greater to mu bar of union EI is something we know because that's a measure which is therefore subadditive. Okay, now so therefore that is greater or equal to, in fact it's equal to here, infimum of mu bar of F, E contained in F, F in S of R. In fact you can show that this is in fact equal. Okay, because I am replacing countable cover by all possible covers from sets. Union EI is in SR, so it's a typical set in SR. Okay, so because it's a sigma ring. Now this again I am going to take infimum over a larger set, so the infimum goes down, E contained in F, and then F is in S bar now. But on S bar, what is this? This is equal to infimum mu star of F, E contained in F, F is in S bar, because mu equals mu bar equals mu star. But then F is greater or equal to E, mu star is outer measure, therefore it's monotone, and therefore this is greater or equal to mu star of E. Okay, so you started with mu star of E, you have again mu star of E, you chain of inequalities, so everything is an equality now, and therefore in particular mu star of E is equal to this one as well as this one. Okay, so that proves the theorem. Now what is the use of this result? Okay, so we now have a ring R and we had a measure mu here. Then we constructed the hereditary outer sigma ring HR with mu star. Then we had mu star measurable sets, and here we have mu bar which is equal to mu star. Then we showed that in fact this contains S of R, and so again here you have mu bar which is a measure. So this is how the Caratheodory scheme works. Okay, so you from R you go to H of R, you go to S bar, then you come to S of R. Okay, so now I can try to play this game again. So I can try to, I have a sigma ring which is a ring and a measure on it, and I can try to find the hereditary sigma ring which contains this, but that will be just H of R because H of R already contains it, and it is the smallest which contains R, so it will also be the smallest which contains S of R. It can't be anything smaller than that. So H of S of R is the same as S of R, H of R. Okay, now by proposition above, if you go look at all the chain of inequalities here, you get that mu bar star of E is the same as mu star of E. So there are the thing is, if you go see, construct the definition, you have mu bar is a measure. If you construct the corresponding outer measure, that is precisely the same as, so we have it here, which is this, and therefore you have nothing different. So it just says that it's the same. So implies S bar for mu bar is the same as S bar for mu. and therefore the measure is still the same. So this construction method is finished once and for all. You cannot try to get something more out of this anymore because of the previous proposition. It completes the entire process. You can't play this game again and again, because if you try to do it, you will end up with the same results. So this tells you that that is the advantage. So now we will use this method to construct the Lebesgue measure. So we have this semi-closed open intervals, semi-open intervals, for which we know you have a notion of a length. Now we have the ring containing all such intervals, so we have to show that that generates a measure on that ring. That is the only job. Once you have that measure, now we apply the Caratheodory construction, and immediately you go to the sigma ring, go to the mu star measurable sets, you get a complete measure, which will be the Lebesgue measure. So this is the idea, and so now everything, all the work has been done. So once we construct the measure, which is nothing but the generalization of length to finite unions of intervals, that's all we have to do. Once we do that, then automatically the Caratheodory method will tell you how to do the Lebesgue measure. And we will see also that you can do simultaneously the same thing. You don't have to work again and again in any space dimension, R1, R2, R3, Rn, and so on. So it's really a very powerful method, and which will give you the Lebesgue measure immediately. So that will be the next thing we do. Of course, before that we will do some exercises based on what we have learnt up to now, and after that we will construct the Lebesgue measure.